Hello, my name is Atef Akarlar, and this is my video submission for the final project for EE456, the Intro to Neural Networks, for the Penn State University. So basically, my project was to train a neural network to be able to create generate music. Basically, what I did was I found a very big database of classical music online, only piano pieces. And I did some data processing on these files. And then I trained a recursive neural network, or RNN for short, on these data. And then I basically made this recursive neural network generate music. So let me go into my code real quickly and show you what it's all about. So basically, I have 4 files here that are basically this whole thing works with 4 files. These are all Python files. I use the PyTorch library. So basically, let me go to the MIDI utilities file first. So basically, if I go here, you're going to see that there's a data set online. This was done for a research paper. I used this data set. It's called the Maestro data set, or MIDI and audio edited for synchronous tracks and organization data set. It is about 200 hours of virtuosic piano performances. And so it is about like 1,000 pieces, if I'm not mistaken. And these are all MIDI files. So if anyone watching this video has done any audio producing, MIDI files are basically the computer way of basically it is a medium where you can do audio producing. Basically, like it's notes. All of these notes have a starting time and ending time. Their pitch is which note they described, and also um, there are some other data. For example, for these MIDI files, they all had an instrument, which was the piano. I chose the piano data set because if there were a lot of instruments, then it would make this much heavier. This already took a very long time to train, and um, yeah, let me just go into my code again and show you how this works. So basically, in this MIDI utils.py file, I do data processing. I'm using this library called Pretty MIDI. It is a library, open source library that allows us to basically extract data from MIDI files and also create MIDI files. So first of all, I download the data set from the internet. If I go down a little bit, then I load this data set into a Python list. Then I process these MIDI files and basically get a dictionary mapping all the file names to the MIDI files or MIDI objects. And then, so this basically took a lot of memory, and because of that, the app would crash a lot of times. So basically, I had to create a cache on the computer. This is my play audio function. It uses the Pygame mixer module to play the MIDI file. If I go down, these are some functions I use to extract the MIDI notes and extract MIDI data. Basically, the name of the instruments. There's only one instrument, but just for scalability, I took into account maybe doing this with multiple instruments in the future. And I have 2 plot functions in this file. One of them is the plot piano roll, and the other one is the plot distribution. Basically, the plot piano roll function plots how these notes would look on a piano layout. So I can show you in the sample file, this one. So basically, all these nodes, there are about 600, 700 nodes in this piece. This is the first piece in the data set. And these are all the locations of these nodes in the piano, if you look at it vertically. And yeah, so let me play this file real quickly so you can see what this sounds like. So if I go here, instead of generated music, I'm gonna say, oops, play audio, and then data slash out slash should be the example file. If I go here, example underscore file.min, and I will be playing this for you right now. Let me. I hope you could hear that. There were some problems with the recording in the past. This is my third time recording this. So then after I do data processing on these files, I go create a recursive neural network function using the PyTorch library. Here's my music RNN class, and you can go into this function in detail. There's a lot of things. Let me talk about why I choose a recursive neural network. Basically, since this is a generative task, and this is a task that depends on what comes before, right? Because basically what the neural network is doing is choosing the node that should play next, depending on which nodes have been played before. Kind of like ChatGPT, but instead of text, instead of speech, it's nodes. So we have a forward function. I used mean square error for the sum of the parts. I use other functions for other parts. These are my training functions, and I have a save model. So basically, there's a lot of nodes in this. If we go into the terminal, I hope the resolution is good enough for you to see. So I am doing all of these in batches because if you look at this, there are a million, is that a million? Yes. There are almost a million nodes in this data set. And it takes a very long time. This is running on very little epochs. I decided to run it in 10 epochs first, but then I settled for 5 because there wasn't a significant amount of improvement in the loss. As you can see, it kind of is stuck around 4, 4.0, 4.8, 4.5. It goes back and forth. The best of these losses is taken into account when the epoch is finally over. And this is it running right now. Yeah, and then I have a dataset file. This is basically where I create the dataset, the PyTorch tensor dataset. That's not too interesting, but what is a little bit interesting here is that I did a little bit of a normalization. If I can find it, yes. So basically, there's a vocab size, and this is for me to normalize. I will talk about other ways of normalizing this data set in the future, towards the end of the video. I think there are better ways of doing this. However, due to the time limitations and also since it would require a lot of algorithms that are not part of this course, I decided to go with normal PyTorch normalization, just squishing the data together between 0 and 1. And if we go to the predict function, this is where all the magic happens. So I have a predict next node function, and I have a generate music function. So basically what happens is the source code should be available for this. You can go look at it yourself. Basically what I do is after I train this data set for 5 epochs, which is not a lot, but it took me on my computer around like an hour or two just to train 5 epochs. maybe there could have been better ways of handling this. I basically concatenated all the nodes of all the pieces, which is why there's a million nodes in the data set. But then we get a model, right? And if we go here inside the file manager real quickly, assignments, final, data, out, and models. So basically, there's 5 epochs, models for the 5 epochs, and there's the best model. So basically, the one with the least amount of loss is chosen as the best model. In this run, fortunately, fortunately is a, I don't know if it's fortunate, but the first epoch was actually the one with the best loss. And let me show you what the output of this is. So if I go to here, not this one, uh, so this is the distribution of all the nodes in this piece. I generated a small piece, around 100 nodes. The previous piece I played for just a couple of seconds, it was 600 nodes. So if I go to the piano roll generated, these are all the nodes. So this, I am aware this looks different from the sample file. Let me put them side by side. As you can see, this is much shorter. There's only around 30 nodes in this generated one. In the other one, there's around 600, 700. However, when you play this, I will say I wouldn't listen to this music myself, but it is something. It is something. Okay, let me just cut this short and play this. So when I run this on VS Code, for some reason, it's not really playing it. So I'm gonna run it from the terminal. So we go here, we import the MIDI utils, the play audio function. As you can see, it's using the Pygame module. And then we say play audio, and I'm just gonna type the address, data, slash out slash generated music.mid. Generated music.mid. And if you play this, you're gonna listen to this amazing masterpiece done by PyTorch by Recoil Networks. And let's hear it, shall we? And I'm gonna cut this short. I mean, uh, it is a piece. It is far from our understanding of. It might be far from what our understanding of a decent piece might be. However, this is a demo, um, and we can train another one. Let's see what the next one will be. So if we run the predict.py again, I'm gonna run it in a different terminal. Let's run it. So it is going to create a um, new piece now. So it is loading all the cache files, generating music, and it says it's playing it, but it's not. If we go back here and run this code again, excuse me. Um, it has created another piece, and if we go to the piano roll for this, it is different. It is similar, but it is different, and the generated distributions is also different. So, what are some challenges I ran into while making this? First of all, I do not know if the way I did it was very efficient. Basically, what I did was I concatenated all the nodes in this 200-hour playlist into one data set and let let the model run a train on it. What could be different? Maybe there could be some other parameters. Um, Another thing that gets me very excited about this, but it's out of the scope of this course. Basically, if you know a little bit about classical music, there are scales. Basically, a scale is the notes, right? So the C scale is the most basic one, and there are some rules. I'm not going to go into too much detail, but what happens is all of these pieces are in different scales, right? So, for example, in one scale, if the note A plays after B, it might sound decent, but in another scale, it might sound very weird. It might sound like abnormal. But a clever way of normalizing this data instead of doing the regular PyTorch normalization could be to transform all the scales into transform all these pieces from different scales into one scale. For example, they could all be in the C scale, they could all be in the A scale. However, I looked this up online. There are algorithms about both detecting scales of a piece and transforming it. Transforming it is the easiest part. Detecting a scale is more complicated. I mean, even professional musicians can tell you that some pieces uh, may seem like they belong in a scale, but actually they're. It is kind of a subjective matter, and I don't want to go too much into detail because it's outside of the scope of this. However, a clever way of normalizing this data instead of PyTorch normalizing would be to basically normalize it by transposing all the pieces from these different scales into one single scale, for example, C scale. If we did that, I think the result could be interesting. I do not know if it will be better, but it's a interesting thing to think about. I want to show something more a little bit something else real quickly, and then this video should be done. So if you go into our predict function, there is so basically we are using a neural network with three inputs because these three inputs are the pitch of the note, basically what note it is. Is it a C? Is it an A? But these are all done with integers instead of like the names of the notes. And the sequence length is basically how many notes are in one sequence. I chose 32. It could be interesting to experiment with different numbers. Maybe like less numbers could be better, more numbers could be better. And then we get an output of 128. What is 128? It is basically not the whole range, but the most of the range, like most of the notes on the piano could fall in this range. So that's why I chose the number 128. And there are some other parameters here. If you go into generate music, if you look at temperature, it basically controls the randomness. If it's a big number, it is more random. If it's a small number, it is more conservative, which is basically there wouldn't be a lot of jumping around the notes. It would be um, notes with less distance. And there's a tempo scale. Basically, when I first did this, the outcome was very fast. So I implemented a tempo scale. What's happening is if the number is bigger than one, it's going to be slower. And if it's smaller than one, it's going to be a faster music. As you can see, I chose two. I think that was the fitting ground for this, the best fit for this. Anyways, I think that is everything. If you want to run this code, the link for the GitHub repo will be available. There are some requirements packages. They're all in the requirements.txt. You can also read the report or the README file if you want more details about this. Thank you very much. I hope the video wasn't too long. And yeah, have a great rest of your day.